Hello, everyone. Hello, hello. Yes, so first of all, I would like to thank you for participating in the webinar. We have to be quick because we have to show you how to build a fully autonomous connected object in 30 minutes. So I will let our two experts introduce themselves.
Okay, thank you, Rais. So maybe we'll start by presenting myself. Hello, everyone. My name is Sadok. I'm the CTO of Dracula Technologies. And what I would like to do today is really to give you an overview of the latest interesting progress of Dracula Technologies, and then to tell you about our inkjet printed flexible organic OPV modules, which are dedicated for indoor applications. But before that, I would like to thank all the organizers of this webinar. And of course, thank you for being here.
Hi everyone, my name is Bruno Damien. I am Ecosystem Marketing Director at e-peas, and my role is to participate and help our partners to develop our ecosystem around the PMICs we manufacture. And during this webinar, we will help you to build your solution based upon our solutions.
Thank you, Sadok and Bruno. I hope that there will be many projects will arise from after this webinar. So, our experts will first start by presenting the purpose of their respective companies before getting to the core of the topic. After that, Sadok will introduce you the sustainable energy source part. And then after that, Bruno will complete the subject with the electronic part after having performed many tests. Do not hesitate to ask your questions. We will have a Q&A session at the end. And Bruno and Sadok, can you disable your camera to ensure a better flow of the presentation, please? And have a good viewing, guys.
Thank you.
Okay, so I will start with introducing our company at e-peas. So we are e-peas, and our company is creating solutions to revolutionize the IoT by offering best performing ambient harvesting solutions for PMICs. So that our, yes?
There is a little problem, so we can see your screen. And can you share your slide presentation, please?
Sorry.
No problem. Sorry for the technical problems. It happens. That's perfect. Thank you.
Okay, sorry. So yes, at e-peas we are doing power management ICs, so that your wireless device can live forever without taking care of energy storage element. So in few words, we propose to the developers our activity to propose use that you can harvest more energy from ambient and consume less energy with your solution, thanks to our ultra low power product and ambient energy management technology. So we work for IoT and smart connected device and even more. So just at the heart of the application, between the harvester source on the left and the storage element on the right, you need an ambient energy manager, an AEM from e-peas. And this device manages and stores the power from the harvester, optimizing the energy transfer from the harvester output to the rechargeable storage element. The PMIC also acts as a main switch for distributing the energy to the application. And we do that with a minimum of losses and a maximum power point tracking. Today we will focus more on solar and light harvesting. And you can see here that we have several products to cover this type of energy. And we will focus essentially on the first one, AEM10941, that we have used to create an EVK together with Dracula Technology. So that's my introduction. I give it to you, Sadok.
Thank you. Just so you allow me to share my presentation. So good. So I guess you see my screen. Okay, that's perfect. So here is a brief overview of what we are doing at Dracula Technologies. So we are a company that was established in 2011 and decided to focus on all printed flexible organic photovoltaic devices, as we believe really that this will allow us to start targeting our first and main application, which is the field of Internet of Things. Today, our headquarters is based in Valence, in France, and we are actually growing quite fast. I joined already the company 5 years ago. That time we were around 7 people, and now we have more than 25 people in total. Most of them are scientists. And currently, we are working with different partners to develop our products and implement them into different kind of application. And today, I'm really pleased to share this webinar with one of our potential partners to show you the complementarity of our technologies. We have currently 6 patents for pending, but most of our know-how is actually related to the processing, the ink formulations, and etc., which is really crucial for achieving high performances and, of course, reliable future production of our OPVs. This know-how is kept secret while being well documented and protected. In the future, what we are looking for is really to improve our efficiency and mainly upscaling our technology. Here, I'm basically presenting differences between conventional photovoltaic and indoor photovoltaic. And as you can clearly see, there are key differences that really important to be mentioned. I guess some of you may be familiar with conventional PV, which is basically flat plate photovoltaic. Here where we have solar panels in general on the roof of houses that capture the sunlight and then transfer the energy. It can be either directly to the grid or even into a large battery for off-grid, which are then used to power some appliances, and here through a power management unit, which comprises in general inverter and controller. As you can clearly see in this case, the PV is really large. Here we are talking about some meter square and sometimes tens of meters square. Now focusing on our main application, which is the indoor applications, which is a little bit different, as you can see here in the right figure. On the concept, there is a similarity. The active scale in this case of the device is completely different. No, we are talking about centimeters square and sometimes even smaller than that. In this case, the light is captured from artificial light sources, like for example, as you can see, LED systems, but can be also fluorescent light. And the light will be used to power small devices like sensors. But before that, this light should be collected and then processed into power management units and storage. After that, we can directly power some small devices like sensors, IoT devices, and so on. So the amount of the energy that we can collect is obviously lower than the size, and the size also of the device is really much smaller. Now here, what I'll try to tell you is about the state of the art concerning the OPV. As nowadays, the OPV really start to represent one of the most important alternatives to the silicon technology, but also the most relevant approach for future low-cost solar cells. Indeed, and as you can see from this graph, the power conversion efficiencies exceeding 18% have been already achieved under standard condition measurement with improved photovoltaic parameters. And as you can see here, really from this chart, which is extracted recently from the NREL website. Which is important to know is that recently, OPV technology has become also a very attractive solution, but for indoor energy harvesting, to power low energy consumption devices, like for the IoT components. And this mainly to overcome the limits of the battery. In particular, as you can see here, for indoor photovoltaic, real progress has been observed with a very significant number of publications showing high performances. As you can see here, sometimes exceeding 30%. This spectacular evolution is mainly due to the new materials, the intensity search on specific high-low band gap polymers, because if you try to look of the difference, you can clearly see that for outdoor or conventional POPV, we are in general using materials that absorb the light more than the visible region. And here, it's mainly due to the use of low band gap polymers, which is not the case for indoor application, where people in general are looking for high band gap polymers to be sure that they can absorb the light in the visible region. But also, this evolution is due to the use of new non-Fullerene accepted derivatives, which allows to adjust the energy levels of the NFA molecules to fine-tune the absorption of the complete device to be compatible and much better with indoor light spectrum, like we can see here in the figures. But there is also another parameters that allow to improve also the performances, is the optimal choice of the interfacial materials for the electron transporting layers and hole transporting layers, which can effectively suppress the leakage current, but also to help, let's say, to help to reduce trap-assisted recombination of the device. Now, let's go to a real example. And through this example, which is our meeting room, I would like really to put in context an indoor environment to give you an idea of the lighting levels in order to make differences between outdoor and indoor environments. Here, there's two examples where we have where we opened the windows, and here when we closed the windows. And I tried to look for some different specific position to give you, and we try to measure the luminosity in order to give you an idea about what we can collect inside, for example, a meeting room. Which is important to know that the luminosity varies greatly depending on the location and also the distance from the light source. In fact, if we try to look, for example, at the walls, depending on where you have your light source, the light intensity vary a lot over the wall. And in general, if we try to have an idea, in general, the luminosity at the walls is in general something between 50 to 300 lux. I think it's important to know these numbers because, in general, sensors are usually placed on walls and corners. So now if you try to play around with the lux meter and to try to look at different positions, so here you realize that the light intensity inside does not exceed 1000 lux and can only reach higher values if you approach the light source, for example, or you try to be near to the window. And here we are really happy because our OPV modules are able to harvest energy even at very low lighting levels, as I will show you later. From 10 lux, we are already able to photogenerate and to obtain already good voltage, allowing to power already some IoT devices. So now we try to go directly to our main motivation to work on this field. And if you try to see this graph, nowadays, the Internet of Things had a spectacular evolution with the significant increase in the IoT devices the last year, as indicated in this left graph, with more than 25 billions of IoT in 2021, expected to rise more than this of around 75 billion devices by 2025. A large number of IoT devices require such device to operate autonomously without connection to the grid in order to be sure and to ensure also sufficient flexibility in their placement. In the ideal case, these IoT devices should harvest energy from their environment, avoiding the need to be plugged in or the use of the batteries that would need sometimes to be changed, especially for devices difficult to access, and then limiting their maintenance costs. If we try to see today what we are using in some, let's say, cases with some IoT devices, we can find that the most common battery, for example, used to power autonomous IoT devices are primary battery, such as, for example, alkaline or lithium batteries. But also we can find some secondary batteries, such as lithium ions and also lithium polymer-based batteries. And in general, most of these batteries have a limited lifetime. So in order to overcome the limits of the battery for application that requires a low energy input, the desired solution must have specific and more interesting characteristics, especially in terms of, let's say, lifetime and environmental impact. We need, of course, to have a solution that should be easy to produce. It can be flexible in order to make easier the integration of the OPV with the IoT devices. And also, if we can have also some aesthetics aspect, that can be also an advantage. For example, transparency, if we can obtain free shape devices. But the most important is to have sustainable solutions and then try to develop green technologies. As in general, all the IoT devices or the major part of IoT devices should be inside the building near to humans. And then, of course, we should be careful about that. To meet the energy need of IoT devices with a solution combining this, let's say, this characteristic, Dracula Technologies today offers its layer technology for light as your energetic response. The module resulting from this technology is produced only 100% by inkjet printing technique and have unique advantages. They are flexible, as you can see, thin, use only non-toxic organic materials, no toxic wastes. And today, we can also have various shapes, allowing simple integration in the final IoT products. And we can also guarantee high lifetime. Today, we can guarantee more than 5 years under indoor conditions, but we can go higher than this. And this will depend on the body film we are using and the application. Just to tell you that at least we can already guarantee the 5 years of good functionality of our OPV devices, and which is something very important for IoT world. Here, just to show you some amazing OPV modules. All of them are functional. To tell you that with our technology, today we are able to produce OPV devices with freedom of design. It can be simple, but it can be also complex design. We can also talk about high flexibility, depending, of course, of the size of the device. But with this high flexibility, we are not losing in performances. And more important than this, that we are also able to produce different size of devices. We can even produce some OPV modules with a size of 1 centimeter square, and then it can give us high performances. Let's say high performance compared, of course, related to the size, but we can already power some IoT devices with that. As I mentioned before, we are focusing in indoor application mainly. And what you see here is our current performances that our standard system can offer right now. As you can see, our layer devices are able to harvest energy even at low luminosity levels while maintaining high voltages. In this table, we have only performances from 50 to 1,000 lux. But believe me, even at 1 lux, we are able already to produce some performances and some powers. And we already tested some use cases that needs really a few micro watts. And we are able today to let's say, to power this kind of IoT devices. Today, we have stabilized our manufacturing process with our pilot line, and we are able to produce some thousands of our standard modules per week in a reproducible way. And now the main question is what we can do with the few, let's say, tens or hundreds of microwatts, and what type of devices can we power at low light levels? For example, at 200 lux or 200 microjoule per second. Bruno, do you think that the performances obtained with our standard modules are sufficient to power an IoT device or not? Or if we have to increase the size of our OPVs?
No, unfortunately not, Sadok. Thank you for those numbers, which are very, very interesting. You give the contextual value of what can be done with these cells, and it's very good. So now, what we can do with this is probably analyze how to store this energy. So we say we have about 130 microjoule production per second at 200 lux. We know you have sketched how we can have this lux level inside the room. So it's important to, let me put it in large. Voilà. It's important for us now to see how to collect this energy. And to collect this energy, what we have done with Dracula Technology is we have prepared an EVK that is made of a PV cell, the one that you have shown before, plus a power management IC that will be capable to collect this energy and manage it, store it, and give it to the application. This EVK, you can purchase it at Mouser. It is ready to use. It's a bundle, and you will see how we use it in the next couple of slides. So you see at the center of this EVK, you have a PMIC, an AEM10941, like we said before. And the reason why we have selected this is because this device has some key assets for us today. They are put here in yellow. So important point is the cold start level at 3 microwatts. Just before, Sadok has said that he can collect energy at the level of production as low as this one. So we want to make good use of this amount of energy. We also have an extremely low leakage current at 400 nanoamps because all this little production of energy is precious to us. So we don't want to waste it into the device. We also have device status digital outputs that enable the application to control what's happening, if production is okay, if it is time to connect or not. That's really cool features, and they are available on this device. We have also smart presets. Those smart presets allow you to play with a set of 3 jumpers and to say, well, I want to connect to a little capacitor. I want to connect to a double layer supercap. I want to connect to a sort of lithium small battery. All those are preset in our device so that you can just, by simply moving your jumpers or your resistance, say, this is where I want to work. And finally, we have also put smart LDOs. Smart because there is a state machine in the device that enables the LDO only when there is a certain amount of energy. So you see that you have already a little machine that is capable to make good use of your production. So now let's see how to use this EVK. So you recognize the PV cell on the right, you recognize the kit in the middle, and we have added 2 little elements. On the top, we have put a micro storage element. So you can imagine the size of it is 3 millimeters diameters times 7 millimeters long. So it's as big as a little electrochemical capacitor. And on the left, extreme left, we have put a dummy load. We start with a dummy load. We will go with more complex things later on. So this dummy load is 33 kilo ohms, and it's acting as a sink of 54 microampere hours every second, so that you have something that is simulating a load, an application that you want to connect. And you see in the middle the famous preset. We provide storage element protection, as you can see. There is over discharge protection, overcharge protection, there is charge ready, and really the device will work between those 2 extremes. So that's one of the very important things for us today. So now we know how to produce, how to store. what can we store? So let's consider that we produce at 200 lux, and we want to store in a storage element that is this capacity on the right. You see that you can capture a lot of energy in a little amount of time. Of course, you can use a smaller electrochemical capacitor, supercap, and so on and so forth. But you will get less energy in faster time. Yes, you can. So it's up to you at the end to define whether you want to have more energy and wait for a longer time before to have your element fully charged. However, at 200 lux, getting a charge time of 4 hours is really small. And we will see in later slides that you can get your part and your equipment working faster than these 4 hours. So let's see now how it works. So what we have is we have a production source that is giving you either 130 microjoules per second, 300, depending on the light condition on the left. And this energy will go to the PMIC to charge the micro storage element. And we have a smart mechanism inside the device that is disconnecting or connecting the LDO as a function of whether we are under charge or charge ready. So when the LDO is disconnected and it is automatically managed by the PMIC, most of the current goes from the PV cell to the micro storage element. That's why you can go fast in charging your element, and we will see with the measurements we have done how fast is this. And once you have reached the charge ready, the level that is ready for use, the PMIC decides it's time to use this energy and to source the load. Here we go through an LDO because we wanted to use this feature. Of course, you can use directly the buck or the boost facility provided by the PMIC. But here we wanted to have an LDO to have a stable reference. So now let's put it under the light. Let's put the system under the light. Here I have a sort of oscilloscope view that is showing on the top in blue the storage element voltage, at the bottom in red what is happening at the PV cell level. So you see the voltage at the PV cell. You see the element is showing some sort of spread of voltage vertically. It's because we have an MPPT function that is shown in the middle. It is tracking continuously where we should be in terms of current voltage extraction so that we get the maximum of energy out of our PV cell. So that's what is shown in the middle, MPPT activity. You see the blue track showing when the LDO is enabled, disabled, enabled, and so on and so forth. So here you see that we are at an ugly situation where at 6 p.m. the evening light is decaying significantly. So at 6 p.m. we have 370 lux going down 15 minutes at 260, and then after 100. And we see that the device is harvesting energy from the PV cell and enabling you to start working with your application after 18 minutes. But after 18 minutes, you connect a continuous load, so you start to decrease the charge of your battery, and the light is going down as well. So at the end, you are at a point where you have almost no more light and a charge that is pulling energy from the storage element. So at this moment, to protect your storage element, the PMIC says stop using it, and we can restart charging. Since it was very low light conditions, I wanted to put some artificial LED lighting. I put 150 lux, and you can see that I restart charging. Then I increase a little my lighting because 500 lux was good enough for working, and I see that I can start continuously charging my element. So once we have done that, we can consider less dirty situation. So we wanted to see what's happening into a normal day. So we put it starting in the middle of the day. So it's exactly the same start time of sort of plot, except that we have extended the storage element measurement. So we see that we start very fast to charge our elements. Then we have the LDO that is connected so that the slope of charge of the storage element goes slower. But still we see that after 56 minutes, we reach the maximum of voltage that the storage element can cope with. So that's quite good in terms of performance. And we see that the MPPT immediately goes slower. Our LDOs are enabled, and we see that we have exceeded the balance of the system where we produce more energy than we can store. So now let's go quickly into first conclusion with this dummy load. With this dummy load, we see that during an evening cold start, we can start after, producing energy and using an application after 18 minutes. And during the morning, we see that we can fully charge our little element in 1 hour. So you see that compared to the 200 lux situation, we go faster. It's normal, we have more light, but it would take us a little bit more if we were at just 200 lux. And at this moment, we have reached 2.7 volt and we have stored 3.4 joules just from light. So what can we do with this? I said earlier that we have a lot of energy, and I will show you that it is really a lot. So what we want to do now is replace this dummy load by a real application. So we are using a Bluetooth beacon that has been designed by a partner on semiconductor, and we see that this small Bluetooth beacon is normally delivered, it's available on the shelf, it's normally delivered with a disposable CR2016 coin cell. And we say at the beginning, and Sadok said it very well, we try to get rid of these coin cells. So we use this equipment and we will see if we can ban. Obviously, you know the answer yet, it's yes, you can. So how do we do that? So we connect the tag, or out of the box, we connect it to the evaluation board through the high voltage output here, which is providing 1.8 volt. We have verified that this is enough for the application to work with. And we connect our little micro storage element, and we get a setup that is looking like this with no coin. Of course, the active area of the evaluation board is just what you see in the center. Now we see what's happening, similar setup as before, but instead of having a continuous 54 microamps, we have a smart device that is taking 10 microjoules for one BLE event, 20 microjoules, sorry, and few hundred of nanojoule per second when there is no activity. So we see that we have a budget here that is quite interesting. Because remember, we store a lot of joules. We store between 2.7 and 3.4 joules, whereas our consumption is just 20 microjoule per event. So we can repeat this 100,000 times. And that gives us a fantastic horizon in front of us for this application. So let's see how it works. Again, we start from a very bad situation. We cold start, we reset the device at 7:55 p.m. with LED lighting in the office. We charge it for 1 hour 40, 1 hour 40, and we see that after 1 hour 40, it's about 9:30 p.m. We switch the light off, we go to bed, and we wait for night time, and we see the sunrise here. And when we monitor the voltage over the element, we see that here the situation is very, very comfortable. We are below overcharging and much above over discharge. So this means that our equipment can work overnight with no light. Obviously, when sunrise is coming, we recreate enough energy, we create more energy, and we can keep working like this forever. To prove it, this is a data log of the application. It's transmitting temperature, moisture level, It's transmitting also atmospheric pressure. It's transmitting the battery level, if it is moving or not. And you see that for each of those dots here, we transmit information to a data logger, and we collect this information, and we see that we forgot the device for 4 days, and it was perfectly working and surviving. One must see that it's triggered by movement. This tag is capable to be activated when acceleration is created on it. There is an accelerometer, so we have continuous monitoring of this situation, and thanks to that, we are capable to activate the device. So you might say, yes, but if I want to continuously monitor, yes, you can. You deactivate the accelerometer, you create your own duty cycle, and you can monitor day and night. The role of this accelerometer is to open the door to making other applications like fall detection, like real-time localization services. There are plenty of applications that require an accelerometer. So we use it, we make good use of it, and we demonstrate here that you can forget your device for 4 days, if not for months, it keeps working. So, as a summary for this, we wanted to show you that taking off-the-shelf products that you can purchase from Mouser, connecting them very quickly using the app notes, you can yet create in less than 30 minutes your IoT device that is working nicely. We just used off-the-shelf products, so now it is you to exercise your creativity using a tiny PV cell, a tiny storage element, combined with high-performance PMIC, smart sensor node. You can create really a battery-free, maintenance-free product running forever. So this work is based upon off-the-shelf products. Our EVK is nice looking and ready for use. And you can replicate the exercise in only 30 minutes. Now it is good to go. I will give back the control to Sadok, because I think, Sadok, you have more creativity to propose to our auditors.
Okay, thank you, Bruno, for this interesting results. I'm really happy to see them again. So from my part, I will try to conclude by giving you some examples, some real examples we demonstrated already with our OPVs. And here I'm basically presenting some products used in different applications that can use our layer modules to provide several functions. Such as, for example, the temperature detectors, smoke detectors, light switch, remote control, and motion detectors, and so on. So we can find different applications and different use cases that really can use our layer technology to power the related electronics. We can even imagine more complex integration, as our modules today are flexible and can be easily integrated. And here, just to finish with some examples for some demonstrator, let's say, or some proof of concept that that used our OPV devices to show you that we can have simple integration. It can be more complicated, and we can even go to some complex design. And in all cases, we succeeded and we demonstrated that our OPV are really efficient and able to already harvest energy under even lighting conditions to power all this kind of IoT devices, which are mainly based on, let's say, environmental sensors. And for these examples, we are mainly using some communication protocols like LoRa or Bluetooth Low Energy or Sigfox or even some other communication protocols. And we demonstrated really that our technology is really efficient and can really give answer to this energy needs. So with that, we finished both presentations, and we will be really happy to see whether you have questions, and we try to do our best to clarify things if it's not clear through the presentation. Thank you very much again.
Yes, So thank you, guys, for your presentation. It was very clear, and we got so many questions for you. I hope you are ready. And we have the first question from Frédéric Sauvage. So he says that on which aging procedure basis you can guarantee 5 years and more lifetimes, and what about exposing your modules to direct sunlight? See, for example, one sun.
Okay, that's good. So yeah, concerning the lifetime, just I will try to clarify something that in general for indoor application and when using indoor lighting conditions, there is no standard today that determine the performances and lifetime of let's say OPV devices. All what's already established is concerned, let's say, other technologies, but mainly for outdoor applications. And here maybe I have two responses to this question. The first one is that we already did some aging tests based on the standard conditions. I mean by that, let's say the aging tests based on lighting, and we exposed our OPV modules during some thousands of hours to sunlight. We did also some aging tests based on temperature from -40 to even to 80 degrees Celsius. We did some electrical stress and so on. And we tried also to estimate the T18 to determine the lifetime of our OPVs in, let's say, the most critical conditions. And then for that, we saw that for outdoor, if we expose our OPVs to outdoor conditions, we have already more than 3 years. We can guarantee more than 3 years. But now we start to have also some good results. And as today, almost we have some modules exposed to indoor environments since now more than 3 years, of around 4 years, and we try to measure them each days and each hours. And when we saw that after 4 years at least, we still have, let's say, similar performances. We have really less than 10% of losses after all these years. So reason why we are confident that we can go more than 5 years, and especially because we have a specific device structure using only 3 imprinted layers. So we have less interfaces. We are targeting materials which are not sensitive to the oxygen, to the moisture, and also are not sensitive to the, let's say, the heating. If we try to increase temperature, we can go even more than 80 degrees. Our devices today are really stable. So for that, we are really confident to give these values and to guarantee more than 5 years with our OPV devices.
Okay, thank you, Sadek, for this
You're welcome.
your answer. I have a question for Bruno now. Jesus is asking, with 380 millivolt and 3 microwatt, how much time does it take to exit the cold start mode?
That's a good question. Let me share with you maybe one table that was shown during this event. I think we have the answer here. So if you look at this here, the minimum starting condition for the device, for the e-peas device, is to have a minimum voltage, which is 350. You see that at 50 lux, you are far above this level, and 3 microwatts of energy. And you see that at 50 lux, you have more than that. So you can even think to reduce the illumination by a factor of almost 5, go down to 10 lux, and you have enough energy to start the device. And let's say that you have a production of Pmax of this. So let's say in less than 1 second, you start immediately to have the PMIC that is up and running.
Okay.
And by the way, if you look at the plot we have taken during the day or during the evening, you see that starting is extremely fast. It's even not a problem. The PMIC itself has an internal leakage current that is about 400 nanoamperes. So if you compare it to what is produced by the PV cell at very, very, very low light, you see that we even do not use this energy for the self-supply of the device.
Okay, thank you, Bruno. I have a quick question for you, Sadok. August is asking what is the efficiency and what peak per meter square?
Okay, so efficiency is let's say the question. It's large. It's difficult to give answer directly to this question because to give you the efficiency of our OPV devices, you should precise before at which luminosity levels and which with which light source we are considering to determine exactly the performances. As I mentioned before, today there is no standard to determine the efficiency exactly. It's not like for the standard PV where we know well that we have specific spectra, and then we have some specific conditions to determine the efficiencies, and then of course we can communicate about different performances and we can compare them. But in the case of indoor application, depending on the light source and depending on the energy level we are talking about, depending on the size and different conditions, then the efficiency can really varies a lot. And then, but just to give you, let's say, a simple answer, we can have efficiencies from 10 to 20%, depending on the light source, the used light source, depending on the level of luminosity. Just to tell you that we are really more efficient in the indoor region. I mean, by that from 1 lux to 1,000 or 2,000 lux, we have similar performances, and we have really high performances in this range of wavelength. But if we go to outdoor conditions, we start to drop in performances compared to other technologies that from the base are dedicated for outdoor applications. So in terms of efficiency itself, I should have some more, let's say, specification on the light source and the level of luminosity, then I can give you more precise response.
Thank you, Sadok. Yes, so we are another question following yours. So does the OPV impact antenna performances in the vicinity and keep out areas required to minimize impacts?
Sorry?
Does the OPV impact antenna performance in the vicinity and keep out the area required to minimize impacts?
I don't think so, because if you try to look to what we're able to produce today and the few energy that we are able to produce, the few count we are able to produce today, I'm not sure that we will generate issues for this. I can give you, let's say, a perfect answer to that, but I think it's not. It doesn't matter. We don't have this risk, I think.
So just to give you an ideas of shape, the antenna of the transceiver is here, is designed here. The PV cell is here. So there is a very limited amount of metal in there. It's mostly isolating stuff. So you can easily think that this type of sandwich or creation here does not create any problem. The radiation pattern of the antenna can be positioned such that there is absolutely no interaction.
Good.
Thank you for your expertise. And so to following some of the other questions, I have one special question for.
Maybe
yes?
Sorry.
Yes.
Maybe if you allow me, but I forgot to answer the question of the, let's say, the power that we can generate with, let's say, watt per meter square. This is the question also. So for that, I think depending again on the luminosity levels, if you are talking, for example, about 1,000 lux, so today we are by using LED system and our LED system, because if we try to use different LED with different temperature of colors and so on, so maybe the story can be a little bit different. But if we try to limit to our system, to our light sources and our and to take, for example, 1,000 lux, we are able to produce let's say power in the range of 35 to 40 microwatt per centimeter square. This is 1,000 lux. Of course, if we try to go to lower luminosity levels, then we will decrease the power. And if you want really more information about this, you can try to have a look to our website, where we propose our demo kit, which is our standard device with all the informations. Then you can find it from 50 to 1,000 lux.
Yes, thank you. Bruno, I have some information, a question from Niklas. He is asking how much lux is required to overcome the power consumption in the EPs, hence charging the storage media. But I don't know if you've already answered it.
Yes, it's similar. It's again the same table. The EPs device, the PMIC needs 400 nanoamps for his own working alone. And we see that we can produce 10 microamps, which is about, if I'm not mistaken, 30 times more at 50 lux. So if I was to divide, I would say that just with 1 lux or 2 lux, you create enough energy to compensate what the EPs is doing. And 0 to 1 lux is not a lot. It's close to night.
Oh.
It's even not the moonlight. It's even less.
Okay. We have a lot of questions. I have to choose some. And yes, I have a question for Sadok. What the maximum power conversion efficiency obtained by your technology layer, for example?
This is the same questions. So today maximum, I can give you, we reached already 21%, but it doesn't. There is no sense to that if we can't compare it to other performances. For example, coming from our competitors, or even coming from academic publications, because we should be careful about the used light source, the condition of measurements. But today we reached already around 21%. But in general, with our, let's say, standard modules, the 6x6, the device that I have here, for our standard devices, we have in general some efficiencies of around 15% today with our pilot line.
Okay, thank you. And can you buy already a couple of your modules? And what will be the advantage to have a module structure that rather than a single cell associated to a DC voltage booster?
Yes, that's a good question. You have to consider the system, the complete system. So the PMIC can act either as a boost or a buck. Boost means you start from low voltage, you increase your voltage, and you go to either your storage element or your application. So you can start with a single cell or dual cell, very low voltage, 0.6 to 1.2 volt, and ask the PMIC to boost up to 1.8, 2.5, 3.3 volt for your application or for your storage element. That's an idea of doing the things. Or vice versa, you take an high voltage PV cell and you use a buck to decrease the voltage of that, store to your element and use in your application. So it's really a matter of what sort of storage element you want to have, what sort of power supply you need for your application, and how do you want to work. Usually, one can say that with a single cell storage element, you may have an efficiency that is a little better. But that, I would say, an area, or let's say a fill factor advantage that is a bit better. Maybe it's a question for Sadok. Once you have defined which type of architecture you want for the electronic, then you can define which type of PV cell you want to use.
Of course, and today, for example, with our technology, which is important to know that here we have real flexibility to produce the modules. We can interconnect them as we want in parallel and in series. We can connect the number what we want of cells. So, and thanks really to our technology, the inkjet printing technologies. And today, just to give you an idea that today the time to prototype is something really very short in our technology. It's something around 1 week. In 1 week, we can design already the device and produce already some hundreds, even some tens of hundreds of units by week. And this is the big advantage of our technology. We have just to define the design and to go directly to the production part.
Thank you. So I think that there is a lot of questions. I will not have time to answer for all of the question, but just can you please Bruno share the slide where we can provide all the different modules and EOVK and
yes, of course.
what I need to create my own autonomous devices powered by ambient light.
So let me show you. Do you see my screen?
Yes, it's perfect.
It's not full screen, but in fact, I don't want to make specifically unique advertising for one company, but it happens that all these elements we have shown today are all available at Mouser. So you can get our EVK here for harvesting energy from Mouser. The references are produced here. You can also get the storage element here from Mouser, exactly the one I am using, and the application as well.
Thank you. We are all agreed that our common enemy here it's the common battery.
Yes, it removes the battery, use a tiny storage element, a tiny PV cell, and puts the batteries to the bin forever.
Yes. Thank you for watching all, and see you on next webinar. I hope so.
Thank you very much.
And yes.
Thank you.
Bye.
Bye-bye.
Bye.